In this video, we are going to finish up the proof of the fundamental theorem of arithmetic by working on the uniqueness part. You should have already been working on some of the uniqueness activities. If you haven't, I encourage you to do that before you continue with this video. Alright, so we're going to look at the uniqueness proof for the fundamental theorem of arithmetic. So first, of course, we're going to review the statement of the fundamental theorem of arithmetic, just to be clear about that. We're going to review our strategy for proving the uniqueness part. And then we're going to list some theorems that we have proved in previous investigations and in the uniqueness activities that are going to help us prove it. And then we're going to prove the darn thing. Alright, so here's the statement of the fundamental theorem of arithmetic. Every integer that is at least 2 is prime or has a prime factorization. We've already proven that. That's the existence part of the theorem. And also the prime factorization is unique up to the order the primes in the factorization are written. In other words, the only way you can get a different prime factorization is taking the same one and just rearranging the order of the prime numbers. So here's how our proof is going to look. We're going to assume that n is equal to p1 times p2 through pm. All the p's are prime numbers. That's one prime factorization. Then we're going to assume we have another prime factorization, q1 times q through qt, where the q's are prime numbers. And so we have where each of the p's and q's is prime, right? We've got to show that m is equal to t. In other words, the number of primes in the first prime factorization is the same as the number of primes in the second one. And we got to show that we can rearrange the primes, if necessary, in each factorization so that they all match up. In other words, each pi is equal to qi. So p1 equals q1, p2 equals q2, p equals 3 equals q3, etc. Now, they don't have to be match up that way initially, but we're proving that if we have to, we can rearrange them so that they do match up like that. So here are some facts that can be useful to us that we've either proven or that's not so hard to see how they'd be proven. So suppose that you have three integers a, b, and c such that the GCD of the first two, a and b, is equal to 1. Then if a divides evenly into b, c, then a divides evenly into c as well. And that is a fact that follows from Bezout's identity that we proved in the activities. If p and q are distinct primes, that means they're different primes, right? The GCD of those two primes is equal to 1. Extremely intuitive, but needs to be proven. That came from the uniqueness activities as well. If you have three prime numbers, p, q, and r, if p divides evenly into qr, then either p equals q or p equals r. That's when we prove directly from the uniqueness activities. And if you imply induction to that reasoning, you can prove that if p, q1, q2, all the way through qt are primes, if p divides the product of the q's, then p is actually equal to one of the q's for some I. So you just use induction on the with the same reasoning that you used in the previous bullet point. So now with those facts, we are ready to prove the uniqueness part of the fundamental theorem of arithmetic. So let's go to it. So here's just the statement of the theorem again, in case you need to refer to it. So with our proof, we're going to assume that we have two prime factorizations, p1, p2 through pm, q1, q2 through qt, where each of the p's and q's is prime. We're going to show that m is equal to t and that we can rearrange the primes in each factorization if necessary so that each pi is equal to qi. And we're going to prove this by induction on m. And remember, m is the number of primes in the first prime factorization. In other words, if it's possible for n to be written as a product of m primes, then the prime factorization is going to be unique. So the base case is when m equals 1. In other words, we can write n as a product of 1 prime. And that just means, well, we have n is equal to p1, and the other prime factorization, the other hypothetical prime factorization, is q1, q2 through qt. Now, n is equal to p1. p1 is a prime. That means n is prime. But if n is prime, that means it doesn't have any factors other than n and 1. However, the product q1 through qt has a bunch of factors other than 1 and n. For instance, q1, q2, all the way through qt. And that means that q1 through qt, that is a composite number, so that cannot be equal to n. So that actually implies that t equals 1. If it equals more than 1, then n is not going to be a prime number. That means that n is equal to p1 is equal to q1. So what happened? We have t equals 1, and so the p1 equals q1 gives us a unique prime factorization. Exactly what we wanted. They're the same length, and we matched up the 1p with the 1q. All right, so for the inductive step, we can assume that any prime factorization with m equals k factors is unique. In other words, if we happen to have p1 times p2 through pk, where those are any k prime numbers, and that happens to be equal to another prime factorization q1, q2 through qt, then k is equal to t, and we can arrange the other primes on the other side so that pi equals qi for all I. And we need to prove that the same thing happens when we have m equals k plus 1 factors. So I just want to note that if we need to, we can change the order of the primes. That does not change the prime factorization, if it happens to be convenient. So here's our setup. Suppose that your prime factorization with the p's is equal to the other prime factorization with the q's, and you have k plus 1 factors on the left. So first of all, notice that p1 divides evenly into n, but n is equal to the product of q1, q2 through qt, which means that p1 divides the product of q1, q2 through qt. By one of our little helper theorems from one of the previous slides, that means that p1 has to be equal to one of the primes in the other prime factorization. So p1 equals, say, qi for some I. So we're going to rearrange the order of the primes on the right-hand side factorization, the one with the q's, so that the qi comes first. In other words, we're going to let qi be q1, so that means that p1 is equal to q1. And if we substitute that in, that gives us p1 times p2 all the way through pk plus 1 is equal to p1, which remember used to be q1, times q2 times all the way to qt. And then we can use our cancellation laws. Remember, we had a cancellation law using some factorization techniques that meant when we had the products on both sides, if we had a common factor, we can cancel it out. So we're going to cancel out the p1s on either side to get p2 through pk plus 1 is equal to q2 through qt. So let's look at that product. The left-hand side of the equation, actually, it used to have k plus 1 factors when it had the p1 in there. Now, since that canceled out, it only has k prime factors. That means we can use inductions, because we know that whenever we have a prime factorization with k factors, that factorization is unique. So by our induction hypothesis, the right-hand side has to have t minus 1 factors. I'm sorry, the right-hand side has t minus 1 factors. It used to have t when it was q1 through qt. We canceled out that q1. Now it only has t minus 1 factors. So we have k plus 1, k factors on the left, t minus 1 factors on the right. Since the prime factorization is unique, that means k is equal to t minus 1. But also that means we can rearrange the prime factors on the right-hand side so that pi equals qi for all I greater than or equal to 2. So between 2 and k plus 1. But remember, we also had p1 equal q1 from before, right? That was the first one that we proved that was the same. That means that pi equals qi, not just for I greater than or equal to 2, but for all I. And remember, we had k is equal to t minus 1, but if we add 1 to both sides of that equation, we get k plus 1 equals t, which means that the number of factors that we have on the left, k plus 1 of our original prime factorization, is equal to the number of prime factors on the right, which was t. So our prime factorization is unique, and that is the completion of our proof. All right, so now we've finished proving the fundamental theorem of arithmetic. The next video is, and instead of activities, it has to do with primes and other number systems.